In the last video, we talked about different types of semiconductors. In this video, we're going to look at an application to electronics, a field in which band theory is of considerable importance. So the first thing that we're going to look at is something called a diode. A diode is essentially a p-n junction. So in other words, you take a p-type semiconductor and an n-type semiconductor and you put them right next to each other. So what I'm going to draw over here on the left is a diagram of the n-type semiconductor and the p-type semiconductor before they come into contact, or the moment they come into contact, before any electrons could possibly move through them. So in both cases, they have a valence band, which is down here on the bottom. And in both cases, they have a conduction band. And if we assume that they are both some form of doped silicon, for example, then those bands will have the same energies as each other. So we've got valence band down here, and we've got conduction band up here. And then the n-type semiconductor also had a donor band that was filled, and the p-type semiconductor also had an acceptor band that was empty. So this guy down here is our donor band, and this guy down here is our acceptor band. Now, looking at those diagrams and thinking about what we know about electrons. Electrons like to be in the lowest energy that they can possibly have. So they're going to be looking for the lowest energy states possible. As soon as that n-type semiconductor and that p-type semiconductor come into contact, we should expect that the electrons in this donor band here are likely going to want to drop in energy down to that empty acceptor band in the p-type semiconductor that it's just come into contact with. And so what that's going to lead to is a net flow of electrons from the n-type semiconductor over to the p-type semiconductor. And what's going to happen then is we're going to build up a negative charge over on the p-type semiconductor side, and there will be a positive charge left behind over on the n-type semiconductor side. And if we just leave those two semiconductors stuck together, not attached to any sort of external circuit, then that's pretty much what's going to happen. The charge separation will build up, and the electrons will stop moving because electrons don't generally like to travel towards things that have a negative charge. If, on the other hand, you connect to an external circuit, whether or not anything happens is going to depend which way round you put your diode in, because current can flow through this one way and not the other way. If you set up your circuit such that electrons are going to come in through the positive end and come out from the negative end, well, that's completely allowable. That's completely reasonable. Current will be able to flow. If, on the other hand, you try to set up your circuit such that the electrons come into the negative end and come out of the positive end, well, that's not going to work. That's not how the charges are going to allow this to happen. So what you've now done is you've actually built a device that allows current to flow through it in one direction, but not the other direction. And that's a very basic but essential requirement of building electronics, is being able to control the direction of current. There is one situation in which you could make the current go the other way, and that is if you provide an external energy source. If you provide an external energy source such that the electrons are able to be excited from the acceptor band that's now been filled up in the p-type semiconductor over toward the n-type semiconductor. If you can get the electrons flowing that way because you've input enough energy to allow them to do that, now the current can flow in the opposite direction. And this is what happens in what we call photodiodes. This is one way of us harnessing energy from the sun in solar cells, is taking that light energy, using that light energy to excite electrons in the reverse direction from which current would naturally flow, and essentially store electrical energy. That's how a photodiode works. It's the same logic as the regular diode. The only difference is we have now allowed for the input of energy from an external source, in this case the sun, that allows the electrons to be excited up into higher energy states, and therefore